Hello everyone, my name is Richard Schneeman and I want to talk to you about the scariest thing a Ruby programmer can face. Wait a second. You hear that? Everyone, run! Oh no, oh no. They're right behind me. There are more of them. Ah! Whew, okay. All right, okay. So actually, there's something even scarier than being chased by dinosaurs. It's syntax errors. Just look at this unexpected syntax error. It's horrifying. Where's the problem? No matter where the problem is, the error always shows up on the last line. Seriously though, where's the problem? What if we had some way to turn the dreaded dead end into something a little bit more obvious? All right, you see the error now? Doesn't line 5 look a little suspicious, like maybe it's missing a do? Okay, question time. Which do you prefer? Do you like this one? Syntax error on the bottom? Where's the problem, you know? Or do you like this one? Yeah. All right, so I did a very scientific study on time lost to syntax error exceptions. I found the average developer loses 100 hours of productivity due to these errors. When I asked developers what they wish for most in life, 78.3% of them told me they wanted an AI algorithm to tell them where their syntax errors are. Well, today you can have that all for the low cost of free with gem install deadend. The deadend library is released on RubyGems, and today we'll be talking about how it works. Well, what all can deadend do? When you miss a keyword like if, do, or def, deadend finds the problem. When you miss an end keyword, deadend finds the problem. When you miss a curly bracket, deadend finds the problem. When you miss a square bracket, deadend finds the problem. Have a problem with a missing pipe character? Deadend finds the problem. Have a problem with a missing Marvel Universe comic book character? Unfortunately, deadend cannot find can't do everything, but we tried. All right, so today we're going to be digging into deadend. We're going to be looking at why syntax errors are especially difficult in Ruby, how to parse and lex code with Ripper, how AI pathfinding algorithms work, and we'll put those all together to build deadend at a high level, and then we will crack open the cover and see how it works at a low level. This is a warning. We're going to get technical. There's going to be a lot of code. But first of all, who am I? Well, why should you listen to me? Well, I go by Schneems on the internet. If you forget how to pronounce my name, you can go to my blog, schneems.com, and on my About page, I have an audio recording of me pronouncing my own name. I created CodeTriage.com, which is a platform for learning how to contribute to open source. On CodeTriage, I've got about 60,000 developers who have signed up to get better and start their open source journey, so you can go CodeTriage.com today. In addition to that, I'm writing a book on how to contribute to open source as well. For details, you can sign up on my blog. I've got a mailing list. You can also sign up on CodeTriage. I will be emailing out to CodeTriage and my list whenever I'm done. When I'm not working on open source or teaching people how to open source with CodeTriage, I like to get paid. I work at Heroku. Right now, I'm working on Salesforce Functions. It is an easy way to work with the data you've got inside of Salesforce using whatever languages you love. Right now we're beta testing with Java and JavaScript users. We'll be rolling out Ruby support later. So if you use Ruby and also Salesforce, I would love to hear from you. My DMs on Twitter are open. People also tell me that I am an exceptional programmer. My programs generate a lot of exceptions. I love exceptions, though, especially when they help me. Okay, name error. All right, this is beautiful. Did I mean to use chdir? Yes, this error brings me joy. The did you mean gem is, are now integrated directly into Ruby is brilliant. But syntax errors in Ruby are just awful. They creep me out. Why is it? Why are they like that? Well, When Ruby gets source code, it needs to Lexing parse it from the top to the bottom, and there are rules about what can and cannot be put in there. For instance, you can't start a Ruby file with an end. That's invalid right away. But what happens if you put in too many keywords or too few? You have too many ends. Well, then Ruby needs to scan the whole file to see if the missing bits are at the bottom. Here's a list of keywords that can trigger a required end. If you have an end statement that doesn't match a valid keyword, then it's going to trigger a syntax error. Okay, what's wrong with this source code? It's missing a do, but Ruby doesn't know that. Ruby only knows that it's got an extra end. Why doesn't Ruby know about that missing do? Because calling chdir with a block is not required. In Ruby, any method can take a block even if it's not used. Here's a method that doesn't take a block when it's called, the bark method. But you can add a block anyway, and it's still totally valid Ruby. Here we're calling it with a block. It doesn't do anything. It just, fluff. But Ruby says, fine, sure, of course, I'll take it. Okay, and this is a fun one. Ruby's syntax rules for parsing are so permissive that while this code can never execute, it's syntactically valid. Note this trailing dot here, and there's also no keyword that ever matches that end. So, this is wild to me. Okay, let's take a look at how Ruby transforms source code into a program. Source code is fed into Ruby and goes through a process called lexing and parsing. You start with source code like this string up here, just hello world. The programming language passes your source code to a lexer. Ruby ships with a parser and a lexer, which is pretty sweet. It's called Ripper. It sounds like it should be the name of a band or something pretty extreme like that. Ripper takes the source code and converts it into tokens with significance. This is the lex output. It will tell you that the type of character that starts the string is a double quote, and the contents are hello world. After the source code is passed through a lexer, it's then fed into a parser where those significant groups are turned into a syntax tree right behind me, and then it's made executable. So this Ruby code over there generates this syntax tree. At this stage, we can detect syntax errors. If the source code is modified to produce an invalid syntax tree, say we cut out one of the lines, then we'll be unable to parse it. In this case, we have orphan syntax nodes that aren't connected to anything, so that's not a valid tree. If a parser can't parse code with invalid syntax, how could we use it for our problem? Well, okay, here's our invalid code again. If we can modify the syntax, for example, commenting out extra code, we can transform the tree to be valid again. In this case, we have actually just removed all of those orphan nodes, and so the tree is now valid. It doesn't do what it originally did, but it's syntactically valid, it parses, it turns into a valid tree again. You can think of this process of transforming invalid source code into valid source code as a recursive tree search starting at the leaf nodes, and we will definitely be using this trick later. All right, quick question. Who knows what AI is? Raise your hand. Type me in the chat. This is pre-recorded. Do it anyway. It's fine. Okay, so artificial intelligence is a fancy way of saying algorithm.
I am more than an algorithm.
Come on. No, you're not.
Fine.
More specifically, AI is a goal-seeking algorithm. That was not the joke. A common example of AI is pathfinding. You want to get from point A to point B. How would you tell a computer to do that? You need a way to break the problem down into discrete actions, normally into nodes, either a graph or a tree. And moving from one to the other will get you either closer or further to the goal. In pathfinding, this would be deciding what turns to take, what roads to drive on. AI needs a goal to know when it can stop looking. For driving, it can stop once the destination has been reached. Games match really well to AI. Okay, here's a chessboard with a famous problem. Get this, it's white's turn to move, it looks like white's gonna lose. Because it's a famous problem, we know a loss isn't inevitable. It is possible to draw the game. That's the optimal outcome for white. But how could a computer figure that out? The computer can simulate possible actions and build up a decision tree that represents the possible moves a player could take for the ready draw, which is the name of this chess problem. The once a tree is generated, the computer can then search that tree and find an optimal outcome. Or it can also build up the tree as it's going, which it actually has to do since there are more moves in chess than you could possibly pre-compute. Chess is not a solved game. All right, so here's an example. Here's the path the computer could take that leads to a loss. Okay. Oh, I'm going to promote that to queen. Oh, that queen got taken. All right, it's a race. Can this pawn get promoted? Up, promoted to a queen. It is checkmate. Black is going to win this. So not a very good outcome for our computer who's playing the white side. All right, here's a better outcome for our computer. The pawn gets taken early. Surprising that this leads to a better result. Oh, okay. It looks like both pawns are taken. All right, and that leads us to a draw. One example of an AI game algorithm for building and searching trees is called min-max. The computer has to build the tree as it goes in order to find an optimal outcome. Even just there's only 2 pieces left at this point in time per player, and this tree is already, can kind of just barely fit on paper. And you might have noticed we actually left out additional steps once we hit kind of the terminal end game. So these trees can get really, really large. The point, though, is that AI algorithms are ones where we don't exactly know how to get the optimal outcome, but we know how to represent the world, and we know how to explore that world programmatically. We're going to put all of this together for the dead-end gem. We talked about how we could think about source code as a tree. We also talked about when we have invalid code, we have an invalid tree. We looked at lexers and parsers. They will tell us when our tree is broken, but we need another way to explore. We need another heuristic. Okay, so this code right here, it's missing a do, but it's ambiguous. Which line needs it? Could be line 1, could be line 2. I can't tell. I could guess. How do we know if we're right or not? But if we have indentation, then it's pretty clear what the intent of the programmer was, that this was supposed to be the block. So we can use indentation and the lexer to recursively comment our code. Now we've got all the tools we need. We've got a combination of parsers and lexers, as well as indentation. And putting all of those together, we can build a searchable tree. Okay, here's a demo of dead end running through an invalid document. This is real Ruby source code with a syntax error that cannot parse. That's what that symbol up there means. When valid code is found, dead end safely removes it. After each step in the search, dead end reevaluates the entire document to see if it's parsable yet. Parsing failed. We need to keep looking. Parsing failed. And again, still failing. Keep going. Keep going. Just keep swimming. Okay. Still looking. Failed. Still invalid. Still invalid. Still invalid. Still invalid. That looks suspicious. The document's checked. The parser reports that this is very minimal document is now parsable. Cool. Syntactically valid. Once that happens, dead end has found a way to transform the document to be valid. It can stop searching the document and instead search the invalid code blocks that it has stored internally. This right here is the actual output that the dead end gem returns on that file. The issue is right here on line 36. It is missing an end statement. It's got def file name, but forgot to add an end at the end of it. All right. That was neat, wasn't it? I think it was neat. I made it, but so anyway, I think it was neat. Okay, so now we're going to take a look at the internals of dead end to see how it actually works. Like all good Ruby libraries, dead end uses monkey patching. Not true. It hooks into require and friends. And then when the syntax error is raised in one of those, then it's passed to dead end. The source code that caused the syntax error is read to disk and then passed into a search object. We use timeout here to ensure that if there's some sort of an accidental infinite loop due to a bug or a pathological slowdown, that the error always raises. I also baked in tracing, which we're going to see the outputs of early on, so that step by step, if you're ever wondering, hey, what is dead end doing? How does it arrive at this conclusion? You can actually see each step, which also allows for debugging, and it makes the end result of the AI not so magical. So you can actually process and see how it does what it does. All right, here's the code search class. Whew. Okay, here's the call. Here's our call method, our main method. Under every great AI algorithm is a while loop, naturally. And in ours, we're using a class called the frontier. It holds all the code blocks that we've generated from the source code. I mean, technically, I guess it's an instance of the class, but you get the idea. The frontier is responsible for checking the exit condition. Here's that logic. If the highlighted lines are on the frontier, the entire document without those lines are checked against the parser. And here's where our parser is actually called. Remember Ripper from before? So this ships with Ruby. We have there's no external dependencies on dead end. It's all just standard library. Okay, let's walk through the logic of searching the same document we saw before from the beginning. Since we saw an invalid, this was invalid source code, the frontier is empty, and so does it hold all the syntax errors? No, because there are still syntax errors in the main document. All right, there are two modes of exploration. We can either add new things onto our frontier, or we can expand an existing block off of the frontier. When do we expand? Well, we can't expand if nothing's there, so that's an easy one. And then for the rest of them, we are going to use indentation to decide when we expand. Essentially, we want to explore the largest indentations first. Right now, there's nothing to expand, so this is false, and we're going to have to add new lines onto our frontier. Okay, the code here is looking at the largest indentation, starting from the bottom and iterating up. We saw this before. This step only uses indentation. If the block that is found is valid Ruby code, then it's more or less essentially commented out. We also saw this before. Boop. The code block is then pushed onto our frontier and our loop continues. All right, we've still not found the problem. Have to keep going. There's still lines with greater indentation, more indentation, so we need to add those first. Looking at the document, this line has more indentation. Boop. Gonna add that onto the same. Gonna run the same process. Comment it out. Add it to the frontier. All right. At this point in time, we've added all the lines at that indentation level, so it's time to expand the frontier. We're gonna call the expansion phase. Here's the expand code. The frontier is stored in indentation order. The highest indentation block is popped off. The block is then expanded using an object and pushed back onto the frontier. Okay, cool. Looks simple, but, you know, I bet there's some complexity in there. How does block expansion work? Well, here's the block expand code. It can either expand more lines at the same indentation level, aka neighbors, or when those are exhausted, it can expand out an indentation level. Both methods use this class, the around block scan, which acts as a DSL for scanning up and down. It ignores previously hidden lines, stops when the lexer detects a keyword pair, such as an if and an end, and then with this method, it peeks around to capture lines at the next indentation level. This line right here at the very end triggers code to perform the scan, and it generates a grouping of lines known as a code block. Previously, we captured this line and put it on the frontier. When it's popped and expanded, it looks around and it finds a matching set of keywords using the scanner. See, it's got an if at the top and an end at the bottom, so it stops looking. This code is valid, so it's hidden. The expanded block is put back on the frontier. All right, back to the top, back to the loop. I do want to pause for a second, though, and talk about two methods that I skipped over in our loop. What are these and why are they here? Well, there's a problem with how I'm lexing the source code that I didn't talk about before. Let's take a look. Remember how I said the block scanner stops after it hits keywords? Well, this is accomplished by a class that represents an individual line in the source code. When that line is created, we lex just that line in order to detect keywords, such as ends or ifs or begin. The problem is that a here doc can contain strings that look like Ruby code but aren't. And without the larger context of the document, the lexer doesn't know that. So here in this case, we are lexing a here doc correctly. We're lexing the entire thing. We can see the here doc begin. We can see the here doc content. But if we only lex the second line without any extra context, then Ripper thinks that this is source code containing an if statement. Essentially, lexing each line doesn't work with here docs. So what are we going to do? How are we going to solve it? My solution to the problem was to delete valid here docs up front. In addition to that, sweeping comments makes the output more concise and helps with detection of any empty lines. Here's how it looks. We got a here doc, and it's gone. Another here doc, that's gone. Another here doc, that's gone. Without going into too much more detail, that's pretty much how the algorithm for search works. Just we keep on iterating, asking, hey, do we expand? Do we add? Do we expand? Do we add? Do we expand? Do we add? And running through those phases until the entire document is parsable and we have built up valid and invalid blocks in our frontier. You can follow the algorithm yourself by running the CLI with the record flag. You'll see an output that has every single step as a new file, and each of those files has the annotated source code. So you can see it looks, kind of similar to some slides you might have seen. All right, once the frontier is done searching, we're not quite done though. The frontier can hold more than one syntax error. Code can hold more than one syntax errors. Look at how many syntax errors this puppy can hold. All right, we want to iterate over all of those invalid blocks stored in the frontier to find the shortest possible order that gives us a valid document. To do that, we create a combination of possible blocks, and then one at a time, we iterate through the combinations in the shortest order. So we look at all of the blocks individually, and then we look at them in pairs, and then we look at them in tries, and then in quads. And check each one to see if it holds the syntax errors. The smallest successful combination is going to be returned. So this is where our search started. Invalid blocks are found. We pretty print to the output using a display formatter. And that's it. Nailed it. So that is dead end in a nutshell. Thank you. Don't leave yet. Okay. So if you are a Ruby developer, then I invite you to add dead end to your gem file. We've got about 300,000 downloads to date. Make it 300,001. Also, while you're at it, hey, sign up for Code Triage. Get started in open source. If you are already started in open source and you're already developing in Ruby, I invite you to check out the source code. Come on to zombocom/deadend on GitHub. Take a look. With this walkthrough, hopefully it should be not too difficult to follow what's going on in the code. Maybe take a look at some issues. Maybe see if you can improve some output. Just play around. If you're a Ruby core dev. So first of all, thank you. Thank you for everything you do. Thank you for coming to Kaigi. Would you consider adding something like dead end? In kind of the same way we added the name error, did you mean gem into Ruby core? Or would you be interested in something like it conceptually? Do you like this code? Do you like this concept? Hey, just let me know. I would love to hear from you. Love to hear more about the approach as well as what you think about the viability of something like this long term. Okay, so today we talked about lexing, parsing, syntax errors, as well as syntax, of course, AI, pathfinding, and goal seeking. But the technical pieces are not what I want you to remember. Okay? The important part is that everyone sitting in this room virtual room is the future of developer tooling. Programming is inherently difficult, but it doesn't mean our tools can't help us. One of the best ways to judge a system is to see how it fails. When we can give care and grace and beauty to our failure modes, then we can create experiences that delight us, experiences that teach us, experiences that elevate our code and our consciousness. A syntax error doesn't have to be an ending. It can be a beginning to a beautiful programming story. My name is Richard Schneeman. I go by Schneems on the internet. I created CodeTriage.com, the easiest way to get started contributing to open source.
I want you to go forth and be an exceptional programmer.
Yeah, be an exceptional programmer. Thank you all for
Bye-bye.
coming to my talk. Zoom wave, everybody. Bye.